All right, welcome back. This is lecture 9, inverse functions. First thing to correct is this is not the exam date nor place. The exam date is Thursday, June 4th, and it is open for 48 hours for you to take online through HonorLock. All right, that's out of the way. Let's continue on. All right, let's look at a quick example, changing from Fahrenheit degrees to Celsius degrees and back. So the function that converts Fahrenheit to Celsius is given by this function right here. All right, what is 50 degrees Fahrenheit in Celsius? Well, let's just find out. See if 50 is going to be 5/9 times 50 minus 32 times 18. This cancels and just gives us 5 times 2, or 10 degrees C. Right? All right. Now, what about 15 degrees Celsius in Fahrenheit? Well, this is reverse, right? So we want to find Fahrenheit, and we want to know when this is 15. Yeah? All right. So multiply by 9 on both sides of the equation. And we get, what's a bigger number? 135 is equal to 5 times 5f minus 32. This is 135 divided by 5 is equal to f minus 32. And what is that? All right, so 135 divided by 5, and that gives us 27 is equal to f minus 32. Add the 32 over, and we get 59 is equal to f. Right? So 15 degrees C is 59 degrees Fahrenheit. So this formula gives Celsius in terms of Fahrenheit. And that was easy for when we plugged in Fahrenheit, but not so nice when we plugged in for C. Inverse functions lets us make that easier. So an inverse function basically undoes what the function does. So if we look at this silly little thing, if you put on your socks and put on your shoes for getting dressed, as you normally would, how would you undress them? How would you undress yourself? Well, 1, remove shoes. And then 2, remove your socks. All right, we did things in the reverse order. Right. So when we talk about inverse functions, what we're doing is we're quote unquote undoing a function. So what does it mean to undo a function? Suppose that f of x is equal to 3x plus 5. What does f do to this input? Well, first off, we are multiplying by 3, right? X is being multiplied by 3, and then we're adding 5, right? So can we construct another function g that undoes f, right? So, well, we do these steps in the reverse order, right? You undo these steps in the reverse order. So if you're adding by 5, instead, we have to undo that by subtracting by 5. And then 2, keep going up. Instead of multiplying by 3, we're going to divide by 3. Okay. So if we look at, let's say, f of 2, right? What is f of 2? F of 2 is equal to 3 times 2 plus 5, which is 6 plus 5 equals 11. So we have f of 2 is equal to 11. Now our g of x, our g function right here, is supposed to be first subtracting by 5. So we have x minus 5, then divide by 3. So you divide everything by 3. If g does undo, f, this is what we'll get. If we have g of 11, we should get back 2, right? So g of 11, that gives us 11 minus 5 over 3, 6 over 3, which is 2. So we get g of 11 is 2. Cool. So this is, you can't see anything. There we go. So this is how you undo a function, right? This is the basics for inverse functions. So now let's go on to that. All right, inverse function, inverse of a function. Suppose that f is a function and g is another function such that f composed with g of x is equal to x for all x in the domain of g, and that g composed with f of x is equal to x for all x in the domain of f. Then g is the inverse of x. So what that means is, so here, f of g of x is equal to x, and g of f of x is equal to x. Right? So that means for f of g of 7, this is going to be 7, right? G of f of negative 2 is just going to be negative 2, right? Because no matter which way you compose them, you just get x back. You get that same input. All right, so how are the domain and range of f and g related? Well, the inputs of f equal the outputs for g. The domain of f is the same as the range of g, and the range of f is equal to the domain of g. Yeah. So these are how the inputs, domains, ranges are related when you have inverse functions g and f. So let's get some terminology going. All right. If g of x is the inverse of f of x, then we refer to it as f negative 1 of x, right? F inverse. We put a negative 1 here. So this is not something you want to confuse. So this is f inverse of x. This is not f to the negative 1 of x. It's not a power. This represents an inverse. Are these functions inverses? F of x is equal to 3x plus 5, and g of x is equal to x minus 5 over 3. Well, to be an inverse, you have to have g of x, g of f of x equal to x, and f of g of x equal to x, right? Well, doesn't matter which one we choose. Let's pick one first. Let's do f of g of x. This is equal to 3 times x minus 5 over 3 plus 5. This is equal to x minus 5 plus 5 equals x. Cool. That's one way done. Now let's look at the other. G of f of x. This is equal to 3x minus 5, or sorry, plus 5 minus 5 all over 3. So this is 3x over 3, which is just x. Right, the 5's cancel and you just get 3x over 3. 3's cancel out and we just get x. So are these guys functions? Yes, these are. What about the other example? F of x is equal to x cubed minus 6, and g of x is equal to x cubed, square root. That's not a square root. Let's take a look at the other example. F of x is equal to x cubed minus 6, and g of x is equal to cubed root of x plus 6. All right, let's look at f of g of x. This is equal to cubed root of x plus 6 cubed minus 6. Well, whatever that is not equal to x. Because when you expand this out, you're going to have an x in there somewhere, but then you're also going to have a residual cubed root of x and a constant deal with. So either way, it's not equal to x. So this guy is not, these guys are not inverses. Okay. So now to talk a little bit about what I just said with f to the negative 1. That is not what we have. Also, yeah, fun little meme. Sorry, it's in black and white. Anyway, f inverse of x does not mean 1 over f of x. To raise a function a power to a power, we're missing a word. To raise a function to a power, use parentheses. So if you wanted to say f squared of x or f of x squared, you would use parentheses as shown here, and that would be f of x times f of x. Similarly, if you wanted to denote 1 over f of x, you would have parentheses f of x parentheses to the negative 1, right? It is a little dangerous that way if you do not do this and you think it means this. All right, so look at this guy. G inverse of x is equal to x minus 5. That is a very bad 5. G inverse of x is equal to x minus 5, while g of x to the negative 1, right, the reciprocal, is 1 over x plus 5. Very different functions. So be cautious. All right. Evaluation examples. Okay, let f of x be that function, 2x plus 7, and let's evaluate some things. Well, f of 3, that's pretty simple. 2 times 3 is 6 plus 7, that gives us 13. F inverse of 13, well, remember that from a few pages ago, we have, I'm going to pull it back. Inputs of f are outputs of our g. Domain of f is range of g, and range of f is equal to domain of g. Right? So in this case, let's look at the first part. Inputs of f equal the outputs of g, and vice versa, right? So the inputs of g equal the outputs of f. So this guy is going to be 3. So what about f inverse of 25? Well, we could write down explicitly the inverse function if we wanted to, or know that this is the output of our original function, right? And then solve for 25 is equal to 2x plus 7. Right? This is the input of our quote unquote g function. This is the input of our inverse, which is the output of our original function. So if we solve for this, we get, is it 18? 18 is equal to 2x, x is equal to 9. So this guy would be 9. All right. Now, what about this table example? G of 6 is going to be 5. G inverse of 1. Well, it's when, so G inverse of 1, so that's going to be 1 is going to be 2. And G inverse of 2, well, that doesn't exist because in the outputs we have no 2 for an output of G of x. Okay. It goes back to that one slide. The inputs of one function are the outputs of its inverse. Okay. So the input of the g of inverse function is the output of the g of x function. G of x does not have a 2, so that does not exist. Well, this brings up an interesting question about existence of inverses. And does every function have one? Spoiler alert, the answer is no. So let's look at f of x is equal to x squared. What would the inverse be? Well, what's happening here? We're squaring. So if we quote unquote undo that / reverse the order of things, we would have f inverse of x equal to the square root of x, possibly. No, not this. So let's see how this fails. If you let g of x equal the square root of x, then g of f of 3 is equal to g of 9, which is equal to the square root of 9, which is equal to 3. And if you have g of f of negative 3, this is, again, g of 9, square root of 9, 3. If I can squeeze it in here, this is g composed with f of 3, g composed with f of negative 3. It's kind of hard to see that I've squeezed it in, but so if you can read that, g of f of 3 is equal to 3, and g of f of negative 3 is equal to 3. So you have a function, g of f, that has two different inputs, resulting in the same output. And that is not a good thing for an inverse. So, right. Let's go on to, we'll come back to that example in a second to find out how we can turn it into, how we can find an inverse out of that function. Inverse relations versus functions. All functions have an inverse relation, and it's just reversing the ordered pairs x and y to yx. This relation is not necessarily a function. So if you look at the inverse relation of this guy, it's just going to be the set of points where we swap x and y. So this is going to be 7, 1, 5, 2, 1, 3, and 7, 4. Clearly, this guy is not a function because you have input going to 1, the same input going to a different output, right? So this is not a function. All right, let's look at the next guy. Inverse relation is again same process. 4, 1, 0, 2, 6, 3, and 1, 4. Right? Inputs going to different outputs. Well, I should say different inputs going to outputs. So this guy does not have the same problem as this one, and we have a function. And because we have a function, we can then say that G inverse is equal to this set of points, if G started out as those set of points. Okay? So let's find out when a function has an inverse function. All right. A function has an inverse, f inverse of x, if its inverse relation is a function. That should be a period, i.e. if each output comes from exactly one input. Okay. A function is one-to-one if it satisfies this condition. All right, so let's look at some examples in these tables. Are these one-to-one? Let's look at this first table. X is 1, 3, negative 2, 4. F of x is 0, 5, 8, 1. Well, this is perfectly reasonable. Each of these outputs comes from exactly one input. All right, now, if we look at the other one, g of x, okay, let's look at the outputs. We got 6, 1, 3, 1. Well, 1 appears twice, and it has 2 different inputs. So I should say this one is yes, one-to-one. And no, not one-to-one. Because these two outputs, they're the same, and they come from different inputs. There's another way to see this /test when a function is invertible. And that is through the horizontal line test. If any horizontal line intersects the graph more than once, then the graph is not one-to-one. A function is one-to-one. If a function is one-to-one, then any horizontal line will intersect the graph at most once. At most once. So if we look at this guy, if we draw a line, well, let's say there. This intersects the graph here, here, and here. So it badly fails the horizontal line test. So this graph is not invertible. Right? Similar idea to the vertical line test, but in this case, it's horizontal. Let's look at a few more examples. F of x is equal to x squared. This one first. Well, doesn't really matter where we draw it, so let's pick here. We intersect the graph once, twice, not one-to-one. Yeah. What about this guy? Anywhere we draw a horizontal line, we only hit the graph once. So this one is one-to-one. And g of x has an inverse. Okay. So those are some graphical examples. Let's look at some algebraic ones. So finding the inverse algebraically. These are the steps that you will use to find the inverse of a function if it has one, right? So first off, check that f is one-to-one. Second, in the equation for f of x, replace f of x with y, then swap x and y in the equation, then solve for y, then check the domain and range of f and f inverse. So step one, check that f is one-to-one. Well, what is this? This is a cubic, as we saw in the last graphic example. The cubic function passed with flying colors for the horizontal line test, so it is one-to-one. Right, so now it's 2. We have y is equal to 2x cubed minus 5. That's part 2. Part 3, swap x and y in the equation. So we have x now is equal to 2y cubed minus 5. 4, solve for y, right? So this is x minus 5 is equal to 2y cubed. X minus 5 is equal to, or over 2, is equal to y cubed. Cubed root of x minus 5 over 2. The cube root of all of this is equal to y. Okay. Now, replace f inverse. So f inverse of x is going to be cubed root x minus 5 over 2. Now check the domain and ranges, i.e., what's the domain of f of x? Well, this is a cubic, it's a polynomial, its domain is all real numbers. What's the range of this guy? The range of this guy is also all real numbers. Cool. And then you would do the reverse, check the domain of this guy, check the range of that guy, make sure they match up, and they do. And so f of x is equal to cube root of x minus 5 over 2 is the inverse of this function. So let us now look at a few more examples. First one, h of x is equal to the 5th root of 2x plus 3. Well, 1, find out if it is one-to-one, and it is. Give out a quick sketch of a 5th root of x function, and it'll pass the horizontal line test. Next, let's replace y with h of x. 5th root 2x plus 3. Swap the variables. X is equal to 5th root of 2y plus 3. Next step is solve. So we have x to the 5th is equal to 2y plus 3. X to the 5th minus 3 is equal to 2y. X to the 5th minus 3 over 2 is equal to y. And now replace with h inverse of x is equal to x to the 5th minus 3 over 2. Check that your domain and ranges are satisfied, which they should be, and that example is done. All right, so now let's look at this function. G of x is equal to 1 over x. Well, is it one-to-one? great. I'm smearing permanent marker all over these pages now. 1. Yes, it is 1-to-1. Well, give out a sketch for the graph, and it looks roughly like this. You draw a horizontal line anywhere along here, and it only hits the graph once. So yes, it is 1-to-1. 2. Y is equal to 1 over x. Swap the variables. And now solve for y. So we have yx is equal to 1 if you multiply this by y on both sides. Actually, here we have x is equal to 1 over y. I'm going to multiply by x on both sides, and we're going to get, not x, sorry, y. And we're going to get xy is equal to 1. Divide by x on both sides. And we're going to get y is equal to 1 over x. This is all provided x is not equal to 0, but we already knew that because of our function g of x is equal to 1 over x. So g inverse of x is equal to 1 over x. Oh. So that one is an interesting little problem. Now let's go on to the graphs of inverses. And notice something a little bit cool. So, are the graphs f of x and f inverse of x related? Well, yes, obviously. But if the point AB lies on the graph of f, then the point, well, again, reverse them, BA lies on the graph of f inverse. What is the result when this is applied to every point of f? Well, look at this function, right? So this is what? 2, 1. That became 1, 2. We look at -2, -1. That became -1, -2, right? And we do this all along, so this function turns into this function. Yeah? Well, there's a nice little thing that happens when we do this. What happens is we see that a graph and its inverse are reflected are the same, not the same graph, but they're reflected across the y equals x line. So from the other example, this was f of x, and this was f inverse of x. Right? We had 2, 1, and that became 1, 2. Right? So these points were reflected across the y equals x line. So that's the nice little relation going on for inverse functions in their graphs. Similarly, we had -2, 1, and that got reflected over to -1, 2. Okay. So let's go back to the example with x squared and if it has an inverse. Well, if we try and draw a horizontal line, it fails miserably, right? So if we cut off the graph and ignore that piece, and we restrict f of x to the positive side of the x-axis, that's not a bracket, 0 to infinity, then f inverse of x would be the square root of x. We would have that. So let's do an example doing just this. All right. This is not the parabola of this guy, but instead, it has a vertex here, I believe, and what, 0, 3. It looks something like this. Right? It goes up like that. So let's do the same idea, and it goes like that, yeah? But we want to find out Well, we want to choose a domain on which f of x equals this function is 1 to 1 and find its inverse on that domain. Clearly, if we use the whole parabola, we're not going to have an inverse, so let's chop it off and use the positive side, like in the last example. So let's restrict this function to -2 to infinity, right? -2 onward, so this positive half of the parabola. Is it 1 to 1? Well, yes, draw a horizontal line on this restricted domain, and it passes with flying colors. 2, well, replace y is equal to x plus 2 squared minus 3. Swap your variables. X is equal to y plus 2 squared minus 3. And then solving for this, we would get x minus x plus 3 is equal to y plus 2 squared. Take the square roots on both sides. Square root of x plus 3 is equal to y plus 2. And then finally, square root x plus 3 minus 2 on the outside is equal to y. And so we would have f inverse of x is equal to the square root x minus x plus 3 minus 2 on the outside. And so the domain of f of x is -2 to infinity, which happens to be the range of this guy, and the domain of this guy is the range of f of x. And so we have, oh, yes, I should mention, when we take the square root here, we have plus or minus, but because we're restricting the domain to -2 and onward, we choose the positive half of this norm because you want the upper part of the inverse graph. And also, if you draw y equals x line, right? Our inverse is going to be this function reflected over. Yeah. So it's going to be what? This is -3, -2, -3, -2. And it's going to look something. This is 1, 0, 0, 1. It's going to look something like that, ish. And so there you have it. That's your inverse function f of x. And there we have it. That is the end of this lecture.